All right. Friday. Not many more weeks are left, believe it or not. So, a couple things before we start the presentation. All right, our syllabus. So I've had a couple people ask about the final exam. Syllabus gives the final exam down here on Friday, November 20th. That is not a mistake. All right, because we're getting out on Thanksgiving week, we don't have that entire week to give final exams. So what the university did is started final on Fridays. So you may have a final on Friday, you may have a final on Saturday. I think some faculty were also told that they can also hold some finals on a Sunday, believe it or not. All right, that's what I've heard. That's what I've heard from some other faculty. This Friday, November 20th, is the day of our final exam. Now, the time's going to be a little bit different. So when this was made, I picked the face-to-face class. I figured everyone would be here in lecture hall, all right, to take a paper exam. That is not what has happened. So our final exam's on that Friday, on the 20th, but it's going to be online just like the rest of our other exams have been. All right, that exam's going to go live first thing in the morning. You'll have until a certain amount of time, until the evening, to start the exam. The exam may actually be in two parts, which is, oops, hold on, there it is. Meant to have that up here on the wrong screen. The exam might be in two parts, just like this exam 3 might be in two parts. So what I've normally done with all of my exams is always kind of had that lab section as our last section, and that was like the questions from the lab. And with how the Blackboard exams have worked, I haven't really been able to do that and still randomize the questions. So what I may do is have like the lecture portion of the exam and then have a smaller exam of maybe 15 to 20 questions. At most is probably 20 questions, where it would just be our lab questions. I may also do make that lab and calculations, but our same rules would apply. They both have to be started by a certain time. I'm not making it to where each one's going to be, let's say 2 hours. I'm looking at collectively what those entire lengths, how long I think it would take you to do both of them together. But yeah, November 20th, that is the day of our final exam. You'll be able to take it anytime during that day. The grades would I'll probably get the grades posted in Blackboard, like your final overall course grades, hopefully by that Monday, so you can check it out. All right. So that is number 1. Any questions on the final exam? I'll give you more information as we get there. So right now I can tell you that our final exam, it's on that 20th, on that Friday, and this is our week, the 16th. My plan is to finish our lecture on that Monday and then use that Wednesday to answer questions. I do have a worksheet that kind of like a final exam practice homework, you can say, that kind of reviews the equations that we've done. So like a Hardy-Weinberg question, a marker capture question, dispersion question, some things like that just kind of gets you back to doing some of these equations, working with the equations. So we'll kind of use Wednesday to answer questions, any questions that you may have. That means then you'll have several days to actually prep for that final exam. All right, so that is number 1. Second thing, so Tuesday's lab didn't get to meet, and I made some videos on how to fill out the life tables. And the one thing I didn't really go over was how to start it for our lab. And I had some questions there. So here's this Excel document. So I walked through this on Thursday. I know Cody did the same thing on Wednesday, like how to go about making these tables. So what I've done is in Excel, I've started making the table that looks like this. So I've got my age class, BX column. I've already inputted all of those data. If you didn't know how to get this without appearing as a date, what you would do is use the apostrophe before those numbers, so that way it doesn't reformat it as a date and doesn't tell you October 19. All right, it actually lists it as 10-19. So all of our ages, these are the age classes. Our age category is going to always start at 0 because these individuals haven't lived in a complete age category yet. They have 0 complete ages. This is our X column. So that means all of these values, when it says B of X, this is what is your expected reproductive output in that X age. So this is in our 0 age category, which is 0. This is in our age 1 category, which is 0.3, and so forth. So what we need to do is actually get this column, and the question was, how do I actually do that? How do I start to get those numbers? Oops. So going back to the lab, I have these tables at the back, and this lists how many individuals died and their age of death. Now, the age of death is the actual year. So in this 0 year, they're not 1 year old, they're newborns. All right, they could be 1 month old, they could be 11 months old when they died, but we had 50 females died and 55 males died. So if this is our table of our females, what we have to do is add up these numbers up until or through age 9. So I have a calculator here. So if I just kind of start with our numbers here, we're going to say 50 plus 12 plus 10 plus 8 plus 5 plus 3 plus 4 plus 4 plus 5. Those are all of those numbers here up through the 9 age, or 9th year, and that gives me 101. So 101 is my starting point. That's at 0. And then I have to do the same thing for 10 to 19. So go back to my calculator, clear it, 10 to 19, so I start with 4. So we got 4 plus 1 plus 2 plus 2 plus 3 plus 3 plus 3 plus 2 plus 2 plus 2. And I get 24. So we had 24 deaths. And we're going to have to do that for each group. So this is for the females. I'm adding up, broken down by age, all the way until we get to the 80 plus. And then you can see we had 0 individuals that died because 0 individuals actually made it to that age. All right, in our 70s, we had 6 individuals. So 70 through 79, it's those numbers added up. So this is the DX column for our females. And then what you would do is do it for the males as well. And you'll have the male table to fill out, and our male table is this one, and you'll note that we don't have these last 2 columns that we did on our females. We don't have the BX column because the males don't give birth, and we don't have these last 2 columns because we can't calculate net reproductive rate for the males. All right, so those of you working through the lab from Tuesday, or those of you in Tuesday lab working through these live tables, hopefully you can get to this point. And then I think in the video, I do a pretty good job of actually showing the formulas, and you can pause it and you can actually see the formulas. And if you get it set up so that everything is in the correct row and in the correct column initially, then that same formula that I use in the video will apply for your tables. All right. So if you have any questions, please email me. All right. So let's move on. So we introduced growth equations. We introduced exponential growth, really, is what we introduced. And the exponential growth had those assumptions, right? And all of the assumptions were tied to either making sure that our population stayed the same, so no migration, making sure that our intrinsic rate of growth is constant and is basically we can take the average and apply it to all individuals. And our last one, which was the time lags, because we can't have time lags between mating and reproduction. That's our R is instantaneous growth. All right, at this instant, how is our population growing? But we know that a lot of that is kind of not valid assumptions. If we go out and look at real life populations, we see that there are things that limit our population growth. Sometimes we have time lags, sometimes we have limited space and limited resources. So what we're going to do now is talk about those regulatory factors, because these things are really what's happening out in the natural world. So recall Darwin's theory of natural selection, right? So we said Darwin's theory had 3 tenets, right? What are those tenets? As a quick review for the final. So what is one of those tenets that laid the basis or formed the basis of natural selection? What was the first one? Anyone can participate. I know it was early on in the lecture, but something even if you've had evolution, you probably covered it. Those at home? Okay, heritable variation exists in our population. All right, so that was number one. We have to have variation in our population, and it has to be heritable, right? Just number one. If we don't have variation, then we don't set up the next part of our natural selection. And if it's not heritable, then there's nothing that selection can act. We're not going to see changes in our population. All right, so variation is heritable. Number 2. What's that? Okay, so we have competition for resources. Not only just competition for resources, but competition for limiting resources. All right? So we've got heritable variation in our population. We've got this competition for these limited resources. And then the third part, it kind of forms it all together. Last part. So we've got competition for limiting resources, and then we have heritable variation. If the individuals have the variation that allows them to get those limiting resources better than other individuals, then those individuals are going to win out, leave more offspring, and then that variation will slowly build throughout our population. All right? That's the theory of natural selection. And it was based on this idea that we have limiting resources. And if we have limiting resources, then by extension, our population growth is going to be limited. There are going to be factors that will prevent our population from growing completely out of control. All right? Now, with natural selection, it's always going to favor those best phenotypes. All right? It's always going to favor the best phenotypes, and the best is kind of in that gray area that we can modify a little bit. Now, with this theory of natural selection, what it's doing is picking out that variation that does best at getting those resources, and those individuals then are going to be exhibiting a higher R. So we've started to violate our assumption in that R isn't going to be constant across all individuals. So if we looked at the instantaneous rate of growth here, and let's say I'm at 0.05, everyone here isn't at 0.05. So according to Darwin, each of our R's could be slightly different, and that R is determined by our genetics. Now, selection is always going to favor phenotypes that have that best R because it means we're going to be leaving more offspring. Now, if we have unlimited resources, then our population growth rate is going to follow this equation. This dn over dt is equal to R times n, where our overall population growth rate is equal to our R times that population size. So if either of these increase, if R increases or if n increases, we get a faster rate of growth. And just recall that R is the birth minus the death rates plus our immigration minus the immigration, and these are the per capita rates of growth. So if we know that populations are going to be regulated and that populations do not grow unbounded, then that implies that something is out there, some forces are out there that is having an effect in changing our per capita birth rates, our per capita death rates, our per capita immigration rates, and our per capita emigration rates. Now, it can be only one of these things, or it could be all of these things. But we do know that these regulatory factors are going to have an effect on these rates, and by having effect on these rates, we thereby change the intrinsic rate of growth. So what we're going to talk about are those factors that change this. Well, what are the factors? Well, broadly speaking, these factors fall under the abiotic category and the biotic category. All right, we know these things are going to affect our populations. So abiotic factors are those things like, drought or wildfire or weather, temperatures. All right, all of those things that are not related to a living organism. All right. The biotic factors are those that are related to a living organism. All right, so things like competition, predation, parasitism, disease, all of those are biotic factors. Now, taken together, you can see that both the abiotic factors and the biotic factors are going to affect what we see in our population, or at least the dynamics of their population size through time. So here you can say, abiotic factors, what effect does that have on mortality rates? Well, perhaps we have a drought, and that drought is going to increase your mortality rates. And then we come out of the drought and our mortality rates drop. Well, when you have your mortality rates increase, what happens? Our population sizes decrease and our densities decrease. But then we get out of the drought, and the next thing that happens is we start to get disease. So as disease comes into our population, our mortality rates increase. And same thing then, you get a decline in our population size. But it's not just the drought and diseases affecting mortality rate, it could also affect reproduction rate. So mortality can increase, causing a decrease in our population size, or our reproductive rates can decrease, thereby also decreasing our population size. But normally, we'll see both mortality and our reproduction affected, as well as our immigration rates, and we'll mention those. All right, so focusing a little bit more on these biotic factors, these are these processes that depend on the actions of living organisms. And we already gave examples. I said predators are one, competitors, parasites, pathogens, any mutualistic type of relationship, anything that we interact with. Food supply can also be a biotic factor because perhaps we're eating other organisms. All right, these are all biotic factors. Now, these biotic factors are going to act in either a top-down fashion or a bottom-up fashion. These terms, top-down versus bottom-up, is in relation to the direction of our food chain, or what I would prefer is a food web. Because a chain implies that it's a linear process, and in actuality, it's more of like a web-like process here. So what's the food chain? Food chain is the hierarchical pattern of energy transfer from our producers to the consumers. All right, it's hierarchical pattern of energy transfer from our producers to the consumers. I'm sure you've seen this. I'm sure you've talked about it in grade school, and then in high school, and then probably in the Principles 1 and 2 course. All right, our food chain, or food web, is composed of various trophic levels. And these trophic levels are simply our feeding levels. All right, it's a set of species that feeds at a particular place in our food chain. All right, so our trophic level is kind of more in reference to the consumers themselves, not necessarily the producers. So if we have a food chain, we've got however many levels we have in them. Each level represents a trophic level, where we start with our primary producers. These are your plants. These are your photosynthetic organisms. They're capturing your sunlight, converting it to organic energy. And then you have your primary consumers that are going to be feeding on these producers. So the primary producers created this organic energy, and then it transfers to the primary consumers, and they assimilate it. And then these guys transfer the energy to the secondary consumers. So you have basically your plants as a primary producer, your herbivores as your primary consumer, and then your predators as your secondary consumer. And we can go on. We can have a tertiary consumer and a quaternary consumer. There will be a limit to these, and hopefully we'll talk about it this year right near the end of our class. But know that if this is a food chain, a simplified food chain, then these two consumers represent our trophic levels. All right, so our top-down and bottom-up fashion is in relation to this food chain. If we have top-down control, then what we're saying is this biological factor is having an effect on those individuals lower in the food chain at a lower trophic level. If we have a bottom-up effect, then we're influencing those trophic levels above us. So top-down control is a process in which organisms higher in our food chain control the density and the diversity of the lower trophic levels. So right now we're just only focused on the density, population sizes. But know that it also can affect the diversity, so at our community level as well. Predators regulating herbivore concentrations, that's a classic example of top-down control. So let's see what that would look like. Top-down control and bottom-up control. So a big part of this control mechanism is to demonstrate that our factor, our predator, our food source, has a direct impact or influence on either our birth rates or our death rates or possibly our migration rates. All right? So if we deal with a top-down control method, what we're interested in seeing is if our population sizes change as a result of that biological factor. So what you're going to see is that we have population growth rates. This is later on in our presentation, where over time our population is going to exhibit this type of growth curve, or could exhibit this type of growth curve, where our population grows up basically to a carrying capacity, grows up to an upper limit and stops there. All right? This is in the case of no predator. If we have top-down control, then what we could see is something like this. Where our predator has an effect on the population. Now, what effect does it have on it? Well, note how much slower our population size increases. So when we go from here to here, we see a decrease in R. It's slower. and growing up, and we also see a decrease in K. So this is an example of a top-down control mechanism, where our predator, or in the presence of our predator, our population grows more slowly, and it doesn't reach as high as as those areas without that predator. Has this been demonstrated? Oh yeah, it's been demonstrated out in nature. Pretty easy to set up fences and exclude organisms, all right, exclude predators. So yeah, we know this, top-down control occurs. Bottom-up control is also going to be something similar. But now we're looking at basically the food source as having an effect. And again, we have to demonstrate that if this is actually bottom-up control, that by supplementing food is going to have an effect on our population. So if our normal population is something like this, there's our carrying capacity. That's our normal situation. Then perhaps we go out there and we supplement food. All right, some of you are aware of this. I mean, if you go to animal science, you supplement, you supplement your farm animals, right, with food. I mean, you don't just let the cattle out grazing all the time. You supplement them, right? Why do they supplement it? Because if we have bottom-up control, then food supplements can have an effect by increasing our or increasing our carrying capacity. So we can have an effect by increasing our carrying capacity or increasing our intrinsic rate of growth. Now let me caution you again. In order to show that these top-down and bottom-up factors are actually having an effect on our population, we have to demonstrate an effect on our intrinsic rate of growth or on our carrying capacity, or our third case, which would be dispersal, immigration, emigration. All right? So these are examples of our top-down and bottom-up control and how they might affect our populations. Questions on those, on these figures? So best way to look at these things, again, I've already kind of mentioned it. If you suspect you have bottom-up control, do food supplements. All right, and a lot of times you suspect this just by looking at the natural variation that exists out from year to year. So year-to-year variation in food supply may give us an idea that perhaps there's some bottom-up control. And if you were really interested in doing that, then you can go out and you can supplement food, or you can take away food and see, does something like this happen? Do we get our change? Now, our factors can occur in a density-dependent way or in a density-independent way. Now, in our density-dependent factors, these are going to be those processes that change as a function of our population density. So as our density changes, so do these rates that we're going to be interested in. All right, so the density-dependent factors, several of them out there, several examples. All right, but what these all have in common is that as our population size gets larger, we're going to see a change in either our per capita birth rates, our per capita death rates, our per capita migration rates, or some combination of them. So it doesn't have to be just one thing. It could be two things that it affects. It could be three things. It could be all of them that it could affect. All right? In the presentation, I just focused on birth and death rates. So this graph represents a basic summary of a density-dependent factor. So as our population density increases, you see a decrease in our reproduction, decrease in our per capita birth rates. As our population density increases, we see an increase in mortality rates. All right? These lines change as a function of population density. All right? These density-dependent factors can act in either a bottom-up or a top-down fashion. So a food supply, that acts in a density-dependent manner. All right? The more individuals that are there, the stronger the competition, the less resources there are for every other individual in our population. Predators act in a density-dependent method, acts in a top-down method. So the more individuals that are there, the more likely you're going to have more predators eating you, which depresses your birth rates, possibly depress your birth rates, but definitely increases your death rates. These density-dependent factors are modeled using the logistic growth equation, and that's what these curves are. So the logistic growth equation is similar to our exponential growth model. All right? Similar, but we've added a density dependence term to it. So for this logistic growth equation, the only thing that we're going to be interested in calculating is this population growth rate, dn over dt. That's going to be the only thing that we're going to focus on calculating. Could we predict our population sizes? Yeah, we could. The equation's a little messy. If you want to look it up, you can. Just do a search. Search for density-dependent population growth predictions, I believe. You'll get it. All right? But we're only concerned with this. So what you'll see is that our equation is this. R times n times k minus n over k. All right? R times n times this term here. Now this term here can be broken up. So you can see k minus n divided by k. I can distribute that k to both, and what we get is this, 1 minus n over k. They mean the same thing. We're going to arrive at the same thing. However, I prefer this method because it's easier for me to do it on my calculator. All right? I don't have to use parentheses and then a parentheses for my numerator. I just use my 1 parentheses for this term and then 1 minus my value divided by our k. So what you'll notice here is that we have this r times n. That was a term that was in our exponential growth model. So just remember, our exponential growth, dn over dt, was equal to r times n. That was at the very first slide that we had. That's our exponential growth. And then what we're going to do is if we have our density dependence, kind of what we might have here, we're going to modify growth using this density dependence term. So mathematically, our r stayed the same. All right? R didn't change. But in reality, that's what this density dependence term is doing. It's actually modifying the value of r. All right, so what are these? Well, r is that intrinsic rate of growth. We've seen it in exponential growth. N is going to be our carrying capacity, our current population size. So n is going to change. And then k is the carrying capacity. Our carrying capacity is the number of individuals that can be supported by the resources available to the population. All right, let you get that written down. So our carrying capacity is the number of individuals that can be supported by the available resources. All right, so our resources determine our carrying capacity. In our bottom up, we increased our resources, and that changed our carrying capacity. In our top down, we didn't change our resources. Our carrying capacity is going to stay the same. Instead, what we've done is regulated our population at a level below its carrying capacity. All right, we're gonna talk about those terms: stability versus equilibrium. Two very different ideas. So our carrying capacity is actually determined by the available resources, by the food supply, by the space, and so forth. On our curve, whoops, I guess we'll get to it later. So with this term, we can relate our R to our carrying capacity to see how our population is going to change. So here's the idea. If we're going to assume that our R is greater than 0, so that we have the potential for growth. When we're far away from our carrying capacity, when we are way down here at the bottom of our curve, super far, then what you can see is that our k minus n over k term, or this 1 minus n, this n is really, really small relative to k. So this term becomes pretty much 1, or this term right here becomes pretty much 0. 1 minus 0 is 1, which then means our growth equation, dn over dt, is approximately equal to this r times n, which is that same equation as the exponential growth model. This is the reason why we measure r when our population size is very small. You know, we brought it up on the last presentation, right? And we asked, why did we do that? Right? It's because we don't have those density-dependent factors at work yet. So our population is basically growing exponentially. It allows us to calculate R. As our population size increases, now this term becomes non-zero. All right, so as long as we're still below our carrying capacity, this term is still going to be positive. It's going to be between 0 and 1, basically. And as long as it's positive, then that's going to make this entire term positive, meaning we have population growth. And our population growth is going to continue until we get to our carrying capacity. So if our population size is equal to our carrying capacity, this term here is equal to 1. 1 minus 1 is 0. 0 times any number is 0, which means our population growth rate is 0. So in our curve, we grow up, we're increasing in size, increasing in size, increasing in size until we get to our carrying capacity, and then we stop growing. Now, this is the ideal situation. In reality, population is going to grow and overshoot our carrying capacity. So what happens when our population size exceeds that carrying capacity term? Well, now this term here, this n over k, is greater than 1. 1 minus a number greater than 1 is a negative number, right? And any negative number times a positive number gives us a negative number. So we'll have negative growth. So this graph kind of summarizes that. Here's our carrying capacity. If our population density is below our carrying capacity, then we're going to grow at that next time point. If we're above our carrying capacity, then our population is going to decline to get us back to that carrying capacity. And then a lot of times what will happen is that we're actually fluctuating around this term, this carrying capacity. So we'll overshoot it, and then this density dependence will push us back towards the carrying capacity. If we're under it, then our density dependence is going to allow that population to grow and increase in size. All right, so our logistic growth curve, our carrying capacity is where we're growing. All right, and what we can do is kind of look at our population growth rate. So just like our exponential growth, our change in population size, that dn over dt, is equal to the slope of our line at any point along here. So whatever population size we're interested in looking at, let's say is right here, the slope of our line at that point gives us the dn over dt. So what we see is our slope of the line's pretty shallow. And then it keeps increasing, 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 keeps getting bigger and bigger and bigger until it hits this point. This is our inflection point. And at this point, we've hit our maximum population growth rate. We've hit the fastest our population can grow. Because then, our slope of our line will start to decline, get shallower and shallower and shallower until we get to our carrying capacity where our line is flat and has a slope of 0. We can present this as in another way. So instead of plotting our population size as a function of time, we can plot it as our change in population size as a function of our population size. And we get a graph that looks like this, a parabola. So what you can see is our population growth increases, keeps getting bigger, 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 hits our peak, and then it declines. This peak is at half of our carrying capacity. That's where our inflection peak is, or our inflection point. It's at half of our carrying capacity. Our growth rate declines, declines, declines until it hits 0. At this point here, that is our carrying capacity. At our carrying capacity, we have a population growth rate of 0, a dn over dt of 0. If we're above our carrying capacity, so our population size exceeds that carrying capacity, we're in our negatives. We experience negative population growth. I present both of these because it kind of demonstrates where we should target, what population sizes we should target if we're going for maximum production. And the people that do this are game managers, food production managers, fish farmers. They want to maintain a population size in their ponds that maximizes their production. And a lot of times this production that you're looking for is reproductive output because you're going to have them reproduce, and then as soon as they reproduce, you move the offspring off to a new site and then harvest the parents. All right? Well, what population size is that? It's at half of our carrying capacity. That gives us the maximum rate of growth, maximum population growth rate. Questions on that? All right. So just like with any of our equations, we can do practice problems. So we have an example problem. Yeasts exhibit an R of 0.25. And I ask, I tell you, a vial that we're going to grow our yeast in can hold 1,000,000 yeast cells. And I ask these 3 questions. What's the population growth rate when we inoculate the vial with 1,000 cells? What's our growth rate when we have 500,000 cells? And what's our growth rate when we have 900,000 yeast cells in that vial? We're going to use our equation to answer those questions. So what I'm going to want you to do is go ahead and try to do this on your own. Write out, it's a word problem, so write out what we know, what's given to us in the problem, and then use our equation and substitute those terms into that equation to figure out our dn over dt for each of these. What we'll do on Monday is to review these answers, go over these answers, and see if you got the same numbers that I did. All right? Questions? Don't forget, I think you had a quiz that's due today, right? And you also have that homework assignment. So I did have someone email me about the homework assignment. They put in the numbers and said, hey, these are the numbers I'm getting. It's being marked wrong. So one of those things is for any number greater than 999, I did not include a comma. So like if you did 1,000, it was just 1,000,000. I didn't use 1,000,000. So what I've done is kind of gone back and gave you the possibility that if you did use a comma, then it was marked correct at that time. All right, and what I've done is it's grading, it's keeping the highest score as the homework assignment, so you shouldn't have any problems. I will say, though, that rounding, I didn't round until the very end. All right, so one of the questions, it was pretty close. The decimal was like 0.49, and we're rounding to a whole number. Well, that next number, that 0.4, isn't 0.5 yet. It's 0.4 still, so we don't round up. We keep it at that number, whatever number that is. So If you have a question about it, please email me. But that is also due. And we're going to, geez, ridiculous. It's the ghost of Cavness Hall. That's what it is. Thursday's lab will know that. Doors were creaking for some oddball reason. But anyways, we're going to do this, and then on Monday I'll release practice problems for this density dependence. And you'll have the same thing. You can work through it again on your own time just to kind of reinforce that you know how to do this. All right, if you have questions, please email me. Don't forget, next week's lab, you need to set up those allelopathy containers, all right? And I told my lab that we talked about 2 different plants, but we're focused on a single different variable. So if you chose one plant and did, let's say, leaves versus nuts, or green leaves versus dead leaves, brown leaves, you could do that if you have justification for why that would be interesting. All right? Get those prepared. We get that set up next week. All right. Have a good weekend. Don't scare the little kids that are out there. Or maybe you do want to scare them. Don't scare mine. Guess have